My Lab 3 report. The purpose of this lab is to examine the motion of a mass oscillating vertically on a spring. In this case, the system is the spring and the mass system, as well as the Earth, and the surroundings are nothing. The fundamental principles that we use in this lab are Newton's second law, and also known as the momentum principle, which relates the net interaction between the system and its surroundings to observe the motion of the system. We also use derivations of this principle, such as the velocity and position update formulas. In this case, the only forces in this system are the spring and the Earth's gravitational force. Additionally, we also use the energy principle, and the energy principle tells us that the energy within the system is equal to the work done by the surroundings. And because there are no surroundings in this case, we know that the work done by the surroundings is zero, which means that the energy within the system is also zero. And energy is calculated with the kinetic plus the potential energy. In this case, there are two potential energies, since there are two forces. The potential energy of the spring and the potential energy of the gravitational force. So we add delta K plus delta US plus delta UG to equal 0. So these are the main results of the lab. On the right side, you can see the x position versus time graph. And you can see that the model and the experiment are very similar. However, they do diverge a little bit towards the end, and we will discuss those reasons in a later slide. On the right side, we see that the y position versus the time graph is very different. However, the oscillation periods are pretty similar, which means that the model can predict some part of the experiment, but it's not a great model for the experiment. And there are a couple of reasons for this. One of them could be that the timings of the model data and the timings of the experiment data probably didn't line up. Additionally, it is also possible that there was some sort of human rounding error while calculating the initial velocity, and that the initial velocities of the model and the experiment are different. So the observed motion that we got from tracker, combined with the information in the instructions of the lab, give us a list of initial conditions that we can then input into our code. So we can see that the ball's mass is 0.402, and this was given to us. And using the tracker data, we were able to find the ball's position, and using the tracker data, I was able to calculate the ball's velocity to be negative 0.21 in the y direction. Additionally, from prior knowledge, we know that the gravitational force is 9.8, and the spring constant and relaxed length of the spring were given to us. I also calculated the vector L by subtracting the ball's position minus the spring's position, and then use that to find L hat and S. I also put in the formulas for the kinetic, gravitational potential, and spring potential energy, and then added all of those to get the total energy. So this is our code. First, we started off by redefining our initial energy, since when K, UG, and US get replaced later on, we still need the initial conditions to find the energy changes. So after we did that, we calculated the gravitational and spring force and then added them to get F net. Then we used that to update the position and velocity of the mass. And then we updated the spring. And then we calculated all the energy changes. And here's where we use the initial energy and along with the newly found energy to find delta K, delta UG, delta US, and ultimately delta E. So any errors in this model and in this experiment could be attributed mainly to human error during the center of mass tracking glow script, human error in the calibration stick as well as the calibration length, and any rounding errors while calculating the initial velocity. Additionally, the system is not truly isolated, so there might be surroundings that we are not accounting for. So, is the energy system satisfied? Yes. Since there are no external forces, we know that delta E must be 0. And as we can see in the graph on the right, delta E is marked by the orange line on the graph, and it stays at 0 the entire model. And thus, delta E is always 0, and the energy system is satisfied. So now, if we compare the different oscillation periods, we can see that in the x direction, K would be 5.857, and in the y direction, K would be 6.872. And we can see that the direction of the oscillation changes the stiffness value of the spring. And even if we think back to our own prior knowledge, we know that this is true. If you've ever played with a spring in a pen, for example, you know that it takes a different amount of force to move the spring in different directions. And that is because there is a different stiffness depending on the direction of the spring, as shown in this math here.